we're going to hit like 4 different concepts. And they're not going to be immediately related to each other, except for as much as their properties of functions, and they have something to do with graphs, and they also have something to do with functions independent of graphs. We'll talk about rates of change, the concepts of even and odd, intervals of increase and decrease, and maxima and minima. And the first of these is directly related to something we did with lines last time, so why don't you remind me of this? Tell me, what's the point over the slope of the line through two points, x0, y0, and x1, y1? How do you compute that slope?
Change in y over the change in x.
Change in y over change in x. Cool. And now just give me formulas for those two things.
Was it xo minus x1 over y0 minus, oh, I had that backwards.
Yeah, but change in y better be the thing that has to do with y. How many people would have instead put that? Yeah, tomato, potato though. Well, actually they're the same, so tomato, tomato is the correct expression. Yeah, they're the same, right? This difference from what I had written before in that the numerator is the additive opposite, but so is the denominator. You can cancel the negative from the two. So this is the same. Groovy. So let's use that. So it's an important fact that like straight lines have the same slope no matter where you look. Functions that aren't straight lines don't. They have different slopes depending on where you look, but you can still talk about like the average slope over an interval. So let's do that. All right, so the average slope of a graph f of x, well, here's a function f of x. Oh, maybe let's do the quick sanity check. That pink graph, is it actually the graph of a function? Cool, passes the vertical line test. It fails the horizontal line test, which we haven't stated yet, but that just means it's not one-to-one. It is indeed a function. The average slope of this function, also called the average rate of change, over an interval x1 to y1, so I'll just emphasize that interval as well, x1 to x2. Is the slope of the straight line between the point x1 f of x1. All right, so that x1 just means that this is the x coordinate is x1. The y coordinate comes from the function. So the average rate of change is the slope of that straight line. That seem like a sensible enough thing to call the average rate of change? All right, in this case, you like go down some, but then you go up more, so the average rate of change should be like positive. All right, so there's the picture. Does that look like you could compute the average rate of change just by looking at this picture? What's the average slope of this function over that interval? I hear a 1. Do I hear a second? Nice. Yeah, so let's do it. So the average slope, or average rate of change, is the change in the output value divided by the change in the input value. In this case, it's 1, 2, 3, 4, 5 minus 1, 2, all over this x value looked like it was 1, 2, minus 1. That seems pretty okay? So, once you have a graph, you can compute the average rate of change by just drawing that line and computing its slope as far as so far. How many people actually did the arithmetic to do that computation as opposed to just like counting? How many people just counted? Saw that it went over 1 and up 1? Yeah, so it has slope 1. So just for the sake of doing it in another way, pink is the graph. That function happens to be, that graph happens to be the graph of x squared plus 1. Which maybe that looks reasonable. It looks like x squared, but you go up by 1. Let's do one other computation. Let's do it without referencing the graph. Let's play the average rate of change game. Let's do the computation directly, just using the formula. So if I want the average rate of change of this function over that interval, what do I need to compute? I need to compute the change in the function value. So that's f at 1 minus f at negative 2 all over 1 minus negative 2. All right. So I think we have some computing to do. Let's do the easiest thing first. What does that denominator simplify to?
3.
3. Cool. That's good. So I'm going to wind up dividing by 3. How do you evaluate f of 1 without looking at the graph? I don't know if this thing is a scale or not. I'm not going to show that. There. Without looking at the graph, how do you compute f of 1?
You plug 1 in for x.
Yeah, just plug 1 in for x. We have a formula for f. So let's use that. And maybe you know that it'll just be 2 without doing anything, but minus, same thing, but plug in negative 2. All right. That looks like something that is perfectly reasonable to compute. Yeah, it looks like there are a few things to do, but nothing so bad. 1 squared is 1, plus 1 is 2. Minus 2 squared is positive 4, plus 1 is 5. There. Keep on simplifying. 2 minus 5 over 3 is negative 1? Because it's negative 3 over 3? So, you can compute average rate of change directly from a formula even if you don't have access to a graph. And, well, here's a thing to notice. Since this isn't a straight line, we don't expect it to have the same slope no matter where we look. And indeed we don't. If you use instead that sample point and that sample point, you got a slope of negative 1. In fact, how many people, while I was doing that computation by hand and like crunching numbers, just like drew the straight line and computed the slope? Did it also have slope negative 1? Awesome. Right, it should be like the slope from that point to that point. Yeah, that looks like it has slope negative 1. I can't draw a straight line, but that looks like it has slope negative 1. Neato. Feel pretty good. Let's see what more people want to see. So there are 2 more examples that are just compute the average rate of change of this function over that interval. People interested in seeing one more example? Cool. So, I think here's what I'll suggest. So walk with those around you. Consider the square root function. Find its average rate of change over the interval from 1 to 2. This one will wind up not being a rational number. So if you want to get a decimal approximation, you'll need a machine. sales. There. We'll use that to just check if our answer seems sensible. So, how many people have a numeric value for this average rate of change? Either exact value or decimal approximation. What'd you get?
0.4142.
Cool. Did you also get an exact value?
-1 plus -2.
-1 plus the square root of 2. And maybe you'd want to simplify that to like root 2 minus 1. That's not so important a simplification unless you want to like use the formula a bunch more. Cool. Anyone want to see that walk out by me? Let's do it. So, what's the formula for average rate of change? The change in the output value divided by change in input value. So, at the scale that it's projected right now, is it like readable from the back? Okay. It's the change in the function value divided by the change in the input value x. So how do you compute each one of those? You start by plugging those two inputs into the function. So this will be f of 2 minus f of 1 all over 2 minus 1. And notice f of 2 definitely does not mean f multiplied by 2. You can't like factor out the f or combine the 2 and the 1 in the numerator at all. That doesn't work. Yeah.
Could you do f of 1 minus f of 2?
Yep, as long as you did 1 minus 2 in the denominator. This is the same thing as f of 1 minus f of 2 all over 1 minus 2. All right, so now I guess we have to just compute the things. So f of 2 just means take the formula for f and plug in x equals 2. Or if you want to do f of 1 first, plug in x equals 1. So when you plug in x equals 2, you get the square root of 2. That is f of 2 minus f of 1 means plug in x equals 1, so that's the square root of 1. And then we will divide by 2 minus 1, which I will simplify to 1. So far feel pretty okay? All right. And depending on how absolutely doing anything by hand phobic you are, this is theoretically something you can ask a calculator to now compute. But let's simplify as much as we can before that. So without using a machine, do you just know what the square root of 2 is? I mean, maybe you know a few digits in the decimal approximation, but like, that means you don't know what it is. You know what it's about. So I'm going to leave that root 2 as root 2. I can't do any better without approximating. And it's dangerous to do any approximation midway through a computation. If you start doing approximations midway through a computation, then those rounding errors might stack up in ways that are hard to control. So try to avoid doing that until the very last step. Plus, it's easier to write square root of 2 than is it to write like 1.7707 or whatever it is. Yeah, whatever. Did I say the thing for the square root of 3? Doesn't matter. But I do know the square root of 1, right? What's the square root of 1?
1.
Awesome. Do I need to remember that I'm dividing by 1? No, it doesn't do anything. Oh, cool. So there's the exact value for the average rate of change. That's the same thing as -1 plus root 2. Oh, and I guess I should have known what the decimals were, given that, like, you told me what they were a few moments ago. Does that computation feel pretty okay? Nice. So, this concept of average rate of change is really something that's studied in depth when you start doing calculus. In that it seems much more interesting, instead of talking about the average rate of change of a function, this average slope, to actually say that, like, if you look at this exact number, like, it looks like there is a slopiness there, right? It's about that steep. So what you'll do in calculus is you'll think about this notion of average rate of change, but over intervals that are like really, really small. And over those intervals that are really, really small, you get the instantaneous rate of change. Making sense of all that requires some tools like the concept of a limit, which aren't the purview of pre-calc. So I won't do instantaneous rate of change in any more detail than that. If you want to, there's an extra credit posted at the end of this section about the instantaneous rate of change. People feel good right now? All right. So I think the main thing, like, just to make sure you have the ideas, is on your own time now, go out and look at the web walk. There will be some average rates of change to compute. See if you can. Next two notions I want to introduce. The words even and odd. And just to see how people feel already, if there are no follow-ups in which I ask you what you think they mean, how many people have seen and have some familiarity with the words even and odd? Well, regarding functions, not numbers this time. Cool. How many people, if I were to ask them what it means for a function to be even, have a pretty good idea? Cool, what's it mean?
Just means if it's pointing up and body from the same direction. I don't know how to explain it.
Yeah, so like, if it's pointing up on one end, then it should also be like pointing up on the other one. It needs something a little bit more flexible than that, because like, they could both be pointing down, right? Or they could both be like going straight out. Really what it means is the behavior to the right of the x-axis is the same as the behavior to the left. And I use my right and left instead of your right and left. That's okay. So, there's like the informal thing. A function is called even if, well, that's in terms of the graph, so I'll put it under the graph. It has the same behavior. And I'm putting this above because I'm going to put another thing in this space too. To the left and right of the y-axis. So, I don't know, there's some graphs off to the right. Let's classify them. First one, does that look like it's even or odd? Just by looking at that graph. Does it do the same thing on either side of the y-axis? Cool, that should be even. Second one, does that do the exact same thing on either side of the y-axis? No, it looks like it does the opposite thing. Not even. Bottom one, does it do the same thing on either side of the y-axis? Cool, also not even. Let's write down a formal definition. So this comes down to thinking about like what it means to do the same thing on either side of the y-axis. Like the fact that those two green dots, like those two green dots, the fact that they have like the same y value is what tells you that this thing is even. How do the x values of those green dots compare? They're like opposites of each other. So an even function is a function that doesn't care if you replace the input by the opposite of the input. So a function is called even if f of x is the exact same thing as f of negative x. And let's see if that works out on this function. If I replace that input with negative x, do I get the same output? Yeah, right, squaring doesn't care if the input's negative or not. So that's why this function is even. What about odd? Now that we've said some things about odd, maybe I'll say one more thing about even. So I'll write this one other way, right? I like this statement. It has the same behavior to the left and right of the y-axis. Maybe I'll also say it's symmetric over the y-axis. As in, if you take what you see to the right of the y-axis and reflect it over the y-axis, you'll get what's going on to the left, which seems sensible. What does it mean for a function to be odd? Well, how about this? The function, the graph's off to the right. The first one, f, would you want to call that an odd function? See some heads shaking, so some of you have some idea what odd should mean, because the first one isn't. The second function, would you want to call that one odd? Cool. So you have some idea of what odd means. Bottom one, would you want that to be odd? I see some heads going up and down and some going left to right, so there's some controversy. Only the second of the three is in fact odd. So let's talk through why. So if the first, yeah.
Doesn't it have to be, if I remember this correctly, doesn't it have to be symmetrical?
Yeah, but over what?
The y-axis. No. Wait. Yeah.
Yeah, so let's think about what symmetry we want. Why is this function odd? So it's odd because
Yeah.
this point and that point are related. As it goes up this way, it goes down that way. It has this hump here. It has the exact opposite hump there. So I think the symmetry is, if I pin down the origin, rotate it 180 degrees, is that the same graph?
So it has to go through 0, 0.
Yeah, it's symmetric across the origin. I can take this point and reflect it over the origin. Or pin down the origin and rotate by 180 degrees. In terms of the graph, a function is odd if its graph is symmetric over the origin. Feel pretty good? And let's just see that this bottom one isn't. If I take this, I'll pin down the origin. So keep your copy of the graph as is, and I'll rotate this one 180 degrees. Does that look like the same graph again as you have on your paper? No, it's pretty close though. This one's just that, but shifted up. So this is pretty close to being odd, but it's not odd. Let's think about what this means in terms of something analytic and formulaic. So being odd somehow means that if I take this xy coordinate and reflect it over the origin, I'll get a new xy coordinate. How do the xy coordinates change when you reflect over the origin?
They stay the same.
I think exactly the opposite. Their values stay the same, but they both become negative what they used to be. Right, the x value is exactly the opposite. It's over the y-axis. The y value then also becomes the exact opposite. So a function is called odd if, when I make the input negative, the output becomes negative. Those things written now, hopefully, for the most part, seem familiar, they trigger some sort of memories. I guess if not, it's fine. There's the definitions. Yeah.
What is the bottom one?
Not odd. So this function is even, but not odd. The second one is odd, but not even. This bottom one is neither even nor odd. So unlike whole numbers, a function can be neither even nor odd. In fact, there is a function that is both even and odd. There's only one function that is even and odd, and I won't tell you what it is. It's not necessarily super important, but think about it some. Try to come up with what it is. There's only one of them. Not like right now, unless you really want to get distracted. All right, so let's just do a quick analytic check. We know whether these functions are even or odd based on what happened on the previous page. Let's check. So this first function on the previous page we said was even. Let's see if it's even by seeing what happens when we plug in negative x. And I think I want the negatives away. So f of negative x, let's see what that is. So that'll be negative x, then it gets squared, then I subtract 1. And now I guess let's just simplify. You take negative x and you square it. Well, what simplification do you see there? Does squaring care if the input is negative? Nah. All right, that's like negative x times negative x. Double negative, they cancel. Oh, cool, that's the same thing as f of x again. This sucker is even. Next one, g of x equals x cubed minus x. On the previous page, we decided this one should be odd, so it better satisfy that g of negative x is the exact same as negative g of x. Let's see if that walks out. So, what happens when we plug negative x in there? So, I guess we know how to plug in negative x. Just replace all the x's by a negative x. Be careful with parentheses. It'll be negative x, and then it gets cubed, minus negative x. And in a perfect world, this should just simplify down to negative g of x if it's actually odd. So let's just see what simplifying you see. What do you see? Doesn't have to be deep. Just notice something that simplifies.